Today, we're going to make our own random dot 3D images from scratch. Probably you've seen these in a book like Magic Eye. They sold by the millions. The technical term for this kind of image is an autostereogram. My first memory of a stereogram is actually not in one of these books. Rather, one day, when I was a kid in the 90s, at the mall with my parents, we saw a high-quality, fancy-framed image of some random colored dots. I didn't believe the sales rep as he said, if you defocus your eyes, a 3D image would pop out. But somehow it was true. It took me a few different visits of trying it, but one trip I was able to look past the image, and I was floored when the 3D scene appeared to pop out before my eyes. Surprisingly, we can make these types of images fairly easily if we understand the 3D geometry and computer vision behind them. Let's see. First, we're going to look at the underlying geometry of having multiple 2D views of a 3D object. Then we'll derive the critical equation connecting the depth to the difference in images between each view. And finally, we'll write some code to generate our own 3D stereograms. Let's start with the geometry of 3D. So if you look at something in front of you, like a tree, your left eye and right eye will see it in slightly different places. You can try this with your finger. Hold it a few inches in front of your nose and close each eye in turn. You can see your finger in the left side of your right eye and the right side of your left eye. This situation is what we have illustrated here with our tree. The tree is on the right side of our left eye's image and the left side of our right eye's image. That difference between images is actually enough for us, or your brain, to figure out how far away the tree is. Imagine each image floating slightly in front of each eye like a pair of glasses. If we take the same point on the tree in both images, then draw a line from each eye through that point on each image, where the two lines meet in front of us will tell us exactly where the actual tree is and how far away from us it is. If the real tree were to be further away from us, the corresponding images of the tree in each eye would move apart a bit to match this new geometry. And if we zoom out and move the tree way back, the resulting projected trees are almost in the center of both images. We can measure how similar the two images are by making a copy of the left image and overlaying it on the right image. The distance between corresponding points in this overlaid image is called the disparity, and it is directly related to the depth of an object. When the object is far away, like we see here, the disparity between the two images is relatively small. But if we bring the object closer, the disparity grows much larger. This relationship is the core idea of depth from disparity, which is probably the most important foundational concept in 3D computer vision. To understand the math better, let's build a diagram of what's happening with the relationship between depth and disparity. First, we want to consider our eyes and the imaginary glasses or images floating just in front of each eye. In computer vision, we refer to the distance between two cameras as the baseline. And here, your eyes are the cameras, so in our case, the baseline is the distance between your eyes. If we consider a point in 3D that is at a depth d units away from us, we can start to see the key triangle. To finish the triangle, we draw a ray from each eye to the 3D point. And the point where each ray intersects the image plane in front of the eyes is where each eye will see that feature. Following these lines from the eyes through the image features and to the 3D point is called triangulation, as it creates a triangle. Now to measure the disparity d, we can copy the image in the left eye on top of the right eye's image and measure the distance between the corresponding features in each image. The last value we need is the distance between the viewer's eyes and the image plane, which is called the focal length f. These 3 points, the eye position and the two image points, make a new smaller triangle with the same shape as the original triangle. By the principle of similar triangles, we know that the ratio between the object depth and the focal plane is the same as the ratio between the baseline and the disparity. Rearranging terms, we get depth equals focal length times baseline divided by disparity. This matches what we saw before. The further the depth, the lower the disparity between viewpoints. Hopefully the geometry here feels pretty straightforward, as it's very important. Understanding depth from disparity allows you to create 3D visual experiences in virtual reality and helps drive 3D physical interactions in augmented reality. Depth from disparity is what allows virtual 3D imagery to feel like it pops right off the page. Armed with the key depth from disparity equation, we are now ready to make some random 3D dot stereogram pictures. Okay, time for some source code. Step 1 is to get some random dots. The code here is straightforward. We loop through each pixel, assigning a random value between 0 and 255 to the red, green, and blue channels of the pixel. Because we assign the same random value to red, green, and blue, the resulting noise will be black and white. We can now create a visual disparity by copying the random noise pattern 2 or more times in the image. For example, we can take this group of 140 columns of pixels and make an exact copy of it shifted to the left. Now, if you look at the visible features in the random noise, you can see an exact copy of each bit of noise 140 pixels apart. This is what will create the visual disparity. Assuming you're close enough to the screen, your left eye will see the pixels in the left box, and your right eye will see the same pixels in the right box. And your brain will interpret this all as a single image laying somewhere behind the screen, creating a floating third copy of the box where the two rays converge. If we continue with copies of the image 140 pixels apart, we can extend the pattern to create the same disparity no matter where you look, providing a uniform sense of depth. Our math for depth from disparity assumed your eyes are a fixed width apart and looking straight ahead. In reality, when you look at something close up, like a phone or a computer screen, your eyes swivel inward to see it better, a process called convergence. This is a natural process that helps you see, but with some effort, you can train yourself to control this effect and allow yourself to look at something close while keeping your eyes straight forward as if you were looking at something far away. This is the key to seeing stereograms. For me, this is most easily done by getting in very close to the screen, then trying to look past it. Then I move the screen back slowly while still staring past the screen, and at some point, the 3D effect just pops in. For me, even with this basic image, I can see the background dots separate from the white lines if I look correctly. You'll know it's working if you see a seventh white line or a third eye appear. If you can't do it yet, don't worry. Again, every pixel has an exact copy repeated every 140 pixels to the left to create a fixed disparity. Let's check out the code I used. We have 3 basic steps. First, I initialize 2 arrays, one to keep track of what color each pixel is, and the second to track which other pixel is at the distance away that matches the target disparity. These 2 pixels need to have the same color, so I call this array same. The pixel color vector is initialized to whatever color was in the corresponding position of our random background image, and the same array is initialized with each pixel being the same as itself, basically no constraint. Next, we need to compute the separation between repeated colors induced by the desired disparity. In this simple example, the separation is fixed at 140 pixels, so we update the same value array for the left pixel to note that it has to match the pixel at the address 140 to its right. Finally, we need to actually set the pixel colors of the matching pairs created by the same array. But there's a trick here. We can go from right to left so that the constraints chain. For example, with an image width of 840 pixels and a fixed disparity of 140 pixels, the pixels at an X position of 700 or larger are just set to the background color. Then, when we get to a pixel at 560, it's constrained to be the same color as the pixel at 700. Then 420 is constrained to be the same as 560 and 700, and so on. So eventually, pixels 0, 140, 280, 420, 560, and 700 all have the exact same color, which is what led to the repeating pattern we saw before. But this is just a flat plane. What about creating an interesting 3D image? In that case, different parts of the image will have different depths, like in this sphere. Here's my code to create the sphere depth map. Basically, you loop through each pixel, taking the distance of that pixel from the center of the image. By the Pythagorean theorem, that distance squared plus the depth squared should be equal to 1, leading to this code to compute the depth of the sphere at any pixel position. Okay, so you remember our depth from disparity equation? If we have a depth image, how can you compute the disparity? Rearranging the terms, we get that the disparity between the point where a feature lies in each eye is equal to the focal length times the baseline over the feature's depth, where the baseline is the distance between your eyes, and the depth is read from the depth map image we made before. Given this equation, we can now update our random dot code. Rather than having a fixed disparity of 140 pixels, we'll compute a disparity based on the depth of the current pixel following the depth from disparity equation. And that separation is what is used to constrain this pixel to match the color of a different pixel later down the row. For the example shown here, I use an eye separation of 2.5 inches, a focal length of 5 inches, and assume a display of 72 dots per inch. Okay, so let's check out the stereogram this code makes. Here are some tips for viewing. I suggest staring towards the top of the video. Try to look past the image so your eyes don't converge. For some people, it helps to get close enough to the screen that your eyes can't converge to focus on the image. Then move back slowly until the image pops. You should be seeing our nice big sphere. If that image works, let's try a new one. Here you should see 3 spheres at 3 different heights and depths. For this image, I colored the red and blue values of each pixel to create this nice gradient, but left the green random to create random features for your brain to compute the disparity from. Here's another gradient stereogram where you can see a 3D lightning bolt icon. And here we have a star. For extra fun, we don't have to use a random background. Here I made a nice heart background to show my appreciation for my viewers. And if we run the same algorithm, but using this heart's image instead of the random background, we can have a large 3D heart made from a field of small 2D hearts. Lastly, I made a seasonal fall background. Let me know in the comments below if you can see the thematic 3D picture hidden here. Random dot images may have peaked in the late 90s, but depth from disparity is here to stay. Stereograms help researchers in cognitive science prove that disparity alone can create a 3D effect, improving our understanding of human perception. In computer science, the broader topic here is known as 3D computer vision or multi-view geometry, and the underlying math behind multi-view triangulation and depth from disparity is what is needed to make 3D movies pop or to create the feeling that an object on a 3D TV is right in front of you by sending slightly different images to each eye with the correct disparities. Even technologies like the vision-only self-driving capabilities found in a Tesla use multiple overlapping cameras all around the car, in part so that the underlying neural networks can understand the disparity between images to help estimate the depth of objects around the car. But to get the best results for 3D reconstruction, especially at the high speeds needed for self-driving cars to compute reactions, the geometry of triangulation is often replaced or augmented with a data-driven neural network. But we'll have to cover that in a future video together. For now, enjoy this video here.